In fact, nothing much in it. I mean, why I say nothing much in it is because, of course, they have mentioned a lot of things related to hardware. Some of the things that they have mentioned, in fact, most of the things that they have mentioned, we will be discussing these things in more details because here in the introduction part, it's more like touch and go. Like they have just mentioned those words. It seems the purpose is just for the students to memorize it, which I strongly don't recommend. Uh, it's better to understand a little bit of technology. But some of the I will point it out that some of the things that they have discussed in this part, we will be discussing those things in the subsequent chapters, in the following chapters. So I would strongly suggest that we wait until that point. But let's move in and see what those terms are and how far we can go with these things. So the main four components that we have is CPU, memory, IO devices, and buses. And that looks very much something like this, if you put it in a very simple way, a simple personal computer. And as you can see, these are the IO devices, or sometimes we call them peripherals, computer peripherals. But the peripherals are not directly connected to the bus, because bus is the main cable, a set of cables that carry all the instruction uh, for all sorts of communication between the CPU, memory, and it actually connects the vital hardware, okay, inside your computer. But bus is not directly connected to all these peripheral devices. So basically, whenever you want to use an IO device, these are all IO devices. In fact, you know it. This is an output device. This is an input device. This is a storage device, which basically an IO. You read and write. Same storage device basically works both as an input and an output device. So all these, actually, you can add more. You can add mouse if you want. These days we have mouse, but as many peripherals you can use. But all of them must go through a controller. This is the most important concept. Well, again, we'll talk about these controllers and drivers in the I/O chapter. We have chapter 5, input output, where we will discuss these things in more details. So everything has to go to the controller, which is basically a chip. So why do we need the controller? So basically what controller does, I will try, as I said, I will try to keep it as short as possible to give you a quick idea. What a controller does is to convert the bit streams, serial bit streams. That means a stream of zeros and ones and ones and zeros, or digital signals that you send to all these electronic IO devices. They convert these bit streams into byte blocks of bytes. And all of them, they have a local buffer. They call it local buffer. That means a controller buffer. All these controllers have a local buffer. After converting these byte blocks, this will be standing in the buffer temporarily, will get stored. And now once they're in there, it's a job of the CPU. Now there needs to be a method to alert the CPU. We'll talk about it later. So CPU will be alerted. And once CPU is alerted, CPU's job is to use the bus to transfer these data, these pending data or byte blocks from the local buffers to the memory. And only once they are in the memory, then those things will be processed. And as we said, if you can remember in the last lecture, somewhere in third generation computer, I introduced the concept of CPU bus or computation mode and I/O mode. So CPU basically works switching from CPU burst to I/O burst. CPU burst means when CPU is busy taking care of computations or computation-bound processes, computation, and I/O burst is when it's taking care of I/O bound processes. Okay, so now you understand that CPU will have to stop its computation-related job and use the bus, because bus is definitely one of the most important components. And the bus, system bus, which mainly comprises of three different kind of bus, three buses: data bus, address bus, and control bus. Now, CPU, these buses are always under the control of CPU, at least most of the time. So CPU will use these buses to read from these local buffers and transfer them to memory for further processing. All right. So that is exactly how things are getting interacted. And again, when something needs to be transferred from the memory to the output device, the CPU will be alerted. CPU will use the bus, transfer them to the buffer, and from the buffer, this will be handed over to the monitors. Now, this is something very brief but important for us to understand. And of course, CPU still uses the buses to get in touch with the memory. So the next thing that we are going to look at is CPU. What is inside the CPU? We have, this is the most important one, that basically reads the instructions. We call it PC, or program counter. Then we have a whole bunch of registers. Of course, we have in between stack pointer, PSW. But another important thing are the registers. These registers, they're basically literally general purpose registers, n number of registers. Okay, the more, the merrier. So something like that. If you have more registers, so you basically, these registers are real-time health check. What is going on? Or I should say real-time health monitoring, the system health monitoring. They're, in real time, they're monitoring what is going on in most of the vital parts of the system, and CPU needs to know about that. So they use these registers, keep an eye on what's going on. And the registers, we will get to know, are tiny storage, of course, volatile. You understand the meaning of volatile, just like RAM. Nothing permanent here. Tiny. It is less than 1 KB. It's only for the runtime. It's only for the CPU to know exactly what is going on this very moment. Okay. Then we have a bunch of instruction cycles where we have two different categories, pipeline and superscalar. Pipeline is the most common one, and perhaps many of you know it. The way PC executes line-by-line instructions from the RAM is basically, it goes through a pipeline cycle: fetch, decode, and execute. This is a cycle that keeps going. But a superscalar, we do it in a slightly different way. We do multiple fetches at one time. Multiple instructions are fetched together and decoded together. But before we execute, we need to put them in a holding buffer. Execution is still a one at a time process. Okay? But the fetch and decode can be concurrent. That means together we bring them back, bring them in, and then we put them in a holding buffer, and from the holding buffer we execute them. And finally we will get to know what is system call. Is a very important thing, system call. And we'll be using the rest of the operating system chapters will be using these words which we call here and there quite often. So what we have here is a processor, as you can see, and most importantly, this is the CPU. Inside the CPU, we have two parts. The one is the arithmetic unit, logic unit, and an arithmetic unit, and the control unit. Control unit is where most of the things are happening, because the control unit uses the control bus, the address bus, and also the data bus to read from an address and to transfer the data. So this is the PC. That's the most important. We call it PC in itself as a register. It just reads the instruction from there and transfers the instruction back to the CPU. And that, the way they work is very interesting. This is where the fetch, execute, fetch, execute cycle plays out. And as you can see, right on the top of the ALU in the arithmetic section, you have a whole bunch of general purpose registers. These were the registers that I was talking about. So we have N, literally you can see the N number of general purpose registers. And these registers, as I said, during the runtime, the execution time of the CPU, these are the registers that keep track of exactly what is happening in all the vital parts of your computer system. So that is what this particular register, this set of registers do. And finally, once the instruction along with the address, because they are all combined together later when we go to study memory management, you will see that the instruction, because instruction and address are everything kind of like messed up and mixed up in zeros and ones. So there needs to be a way to differentiate or to identify which part should be considered as an address and which part should be considered as the real instruction. All are in zeros and ones. So that will be done once the instruction is fetched. And then from there, the instruction part will be sent to the decoder, as you can see, and then decoder will decode it and send it to the ALU, or arithmetic logic unit, which is in itself the real brain, the core of the brain, okay, of the computer that does all the computation. So that is how your CPU works. As I said, these are how we pass the instructions. There are two different ways that we read and implement these instructions line by line. The first one is the pipeline, three-stage pipeline, which is the most popular one. In fact, you will see this cycle being repeated elsewhere as well. Maybe we will change the names here and there, change the words here and there, but it's pretty same. Like when you go to study process, right? And there you will see process and database. You will see that we often refer to a cycle, which is very similar to this one, but over there we call it fetch, execute, and update. Think about when you interact with database. You fetch the data, you do whatever you want to do with the data, you get an updated value, but then you have to return it to the server. So in many other parts in computer science, you will see the same thing being repeated. It's the most simple and linear way of repeating a cycle in a synchronous way. Synchronous way means there's a little bit of synchronization, because whenever it is only one at a time, and most of the things that happen inside a computer related to resource utilization is always one at a time. So anyway, right in here, we call it fetch, decode, and execute, a three-stage pipeline, where superscalar is this one, as I said. that you can actually bring multiple instructions at the same point of time and decode them as well. But you need to put them in a holding buffer. And of course, that is where they are stacked up in a linear way, in a sequential way, and then execution will happen up there. Right. So that is, these are the two. For your exam purpose, you just remember the names. Okay? Because the multiple choice questions, these kind of slides help the examiners to quickly write a question. I did it many times for almost 3 years. Now I don't do it anymore because now, everything is done from Hanoi. So before that, when the final exams used to be conducted from the campus, from our campus, I did it for many years. So these kind of slides, pay attention when you read this kind of slides. And this is purely for your exam preparation, the point of view. They're quite handy. I mean, when I look at it and I feel that, oh, I can make a question from there. A tricky question. So pay attention to this kind of slides, the things that you will have to remember. We already discussed it a little bit, the way they work, like user mode and kernel mode. There's a benefit of splitting it up in two ways. The real benefit is that it keeps itself safe, the OS, to protect itself from other system components. Protection. Because first, it has to come, remember, the kernel is the most important. Kernel codes are the important codes. And it's so important that we even saw that we talked about MS-DOS, where it was only the kernel that was given to us, right? When we're talking about mainframe computers. So in monolithic structure, we haven't followed any structure yet, right? Yeah, it will come up later. So we understand the dual mode operation and user mode and kernel mode. The question is, as I mentioned earlier, how does it take place? It happens because of switching of control. I mentioned that word, if you can still remember. They switch the control between them. Okay, asking each other to pay attention to the following task. Now, how do they switch the control? They switch the control by changing this mode bit. Okay, they change this mode bit. Now, what is this mode bit? This mode bits, we have assigned a mode bit. For the user mode, it is 1. For the kernel mode, the core, it's 0. So if user mode wants to pass the control to the kernel mode, the very first thing it needs to do is to change the mode bit from 1 to 0. So that means now it is a kernel whose responsibility is to further execute and do whatever needs to be done. Process the request. That is probably coming from one of these applications. But then again, when it comes to changing, then we have to from the kernel mode, and the kernel mode wants to hand over the feedback back to the user mode. Then it will back to the user mode. It will simply switch it or change it to 1, because 1 is for the kernel mode. Right. So that is how these things play out. How these things play out. So constantly switching the control by changing the mode bit. And that is how it works. This picture, this picture will clearly tell you exactly what is happening. What is happening. As you can see, take your time to study it. As you can see, when we give a system call, we'll talk about system call later. System call is basically a service request that is coming from the user mode to the kernel mode. Okay, and as you can see right here, there's the system call. Its mode bit is 1, its mode bit is 0. It needs to be switched. I gave a trap, mode bit set to 0, kernel jumps in and takes it up and does whatever it has to do with the underlying hardware, gets a response, and now gives a return. And how does it give the return? It gives the return by changing the mode bit to 1. Again, from your exam's point of view, these are little things that sometimes somewhere you can get a question. So please remember the mode bit 0 for kernel, mode bit 1 for user mode. Memory. As I said, is a hierarchy of memory. And this hierarchy of memory is based on speed, cost, size, and volatility. Going back, registers, as you can see, the capacity is less than 1 KB. Super fast, very expensive, and totally volatile. Okay? Cache, less expensive than registers, still volatile, but volatility compared to the registers is less because its capacity is more than the registers, and the typical access time of speed is also a little slow. Up to main memory, so register, cache, and main memory, these three are volatile memories. Magnetic disk and magnetic tape, obviously, that does take time to access the data that you have stored there, and their capacity is larger. And most importantly, these are non-volatile. Okay, typical memory hierarchy. The slides have been created in such a way, these are the new bunch of slides, created in such a way that it is much easier for the examiners to set up some questions, especially multiple choice questions, the kind of questions we use for the final exam. Registers a small number first, capacity 32 by 32 for 32-bit, 64 by 64 in 64-bit. Caching. I think most of you are familiar with this word caching. We use the word cache, right? Everywhere, even internet cache. Well, almost all the apps, they maintain a cache. A cache is a less than 1 MB amount of storage, volatile storage. It doesn't persist. The beauty of cache is why cache is so fast. The cache, for cache, we always say that it physically belongs to the hard disk. Okay, but logically it belongs to the RAM. So in other words, think about your browser. You're using a browser and the browser has the cache. From time to time, for whatever reason, when your browser slows down, then you are supposed to go there and clean the cache. Right. Now, this cache, when the browser is not working, that means you haven't started the browser yet, So does it still have the cache? Yes, it is still stored on the hard disk. But when you start up your browser, along with all the other codes and the components of the browser that needs to be on RAM, the very first thing that will be loaded on RAM is that cache. So essentially, when you are using the cache to access a frequently visited web page, you are not accessing that data from the hard disk anymore. You are actually accessing it straight from the RAM, and that makes it super fast. Okay. Now, copying information into faster storage system, main memory can be viewed as the last cache for secondary storage. Sure. Important principle performed at many levels in a computer, in hardware operating systems, we will find in many places, including memory management, file system management, will be looking at cache, sometimes also referred to as buffer. Okay, the information is used copied from slower to faster storage temporarily. The faster storage checked first to determine if information is there. If the information is not found in the cache in the faster storage, then we move on to do a detailed search on the actual slower storage. We all know the cache size is smaller, less than 1 MB or 1 MB. So naturally, they keep pushing things in and out randomly. Main memory, RAM. The problems are how to protect the program from one another and the kernel from them all. That means the OS, and how to handle relocation. They shouldn't have mentioned it in this way right here in the introduction part without giving the details, because they have given some of the words, they mentioned some of the words of which I'm sure you don't know anything at this stage. But anyway, don't worry. And I'm not going to explain in details those terms right here, because we'll be spending at least weeks on memory management. These are all parts of memory management. Memory management, then chapter number 3, is one of the most important and critical chapters. Okay, so we will talk about all these things in details. If you are following this lecture, just note them down, and you can take note that we will talk about this in more details later. Now, just to give you a quick idea of base register and limit registers, so that is what they have mentioned here. So how do you know? The question is, how do you know where exactly is the code for a particular program? How will CPU know? It's not about you. How will CPU know that where exactly it can find a particular line of code that belongs to process number 1, say, for example, right? Because on multi-computer, multi-programming computers like our desktops, we have a whole bunch of programs, the multiple programs loaded side by side. So they need a sort of protection from one another. To do that, at the very early stage of development in the early computers, we introduced the concept of base and limit. So each program on the RAM must have a base value. I'm trying to keep it as simple as possible. Okay. We will talk about all these things once more in memory management. We'll spend time there. So basically, the thing is the CPU needs to be aware of exactly where the program starts and what is the length of the program. Why it was important? Because in those days, we were always loading the program on RAM, or the program instructions or the codes on RAM in contiguous memory allocations. Take note of these words, We don't do it anymore. Okay. But the early stage, that is what we were doing. We call it, I write it down for you, contiguous memory allocation. That means if this is RAM and if this is the starting point of a program, then the rest of the program codes must be next to each other. So will be, this area will be designated for process 1 on RAM. Not this area, not this area. So to keep track, to understand which program is currently executing or which address belong to which program codes, the codes of which program, then the CPU needed to remember the base value, that is the base, that's the starting point of the program, where the program was loaded on RAM, and the length of the program. Because once you have the starting address, say the starting address is 5, and the length is 5 KB, and each address, the spacing is 1 KB, 1 KB, 1 KB, so 5 to 10. In between address 5 and address, of course, when it comes to memory address, it's not like 5 or 10. It is a 32-bit number, 8-bit number, 16-bit number, 32-bit number, something. But I'm oversimplifying it just to give you the idea of what is base register. So once you know this one, and you add to it the length, and you get the terminal point. So you know between address 5 and 10, anything that is in there in between 5 and 10 must belong to process 1. So this was called the base value, and this length was called the limit value. For all the programs, as I said, there are multiple programs loaded side by side in RAM. For all the programs, there will be multiple base values, B1, B2, B3. All these base values will be stored in a register called base register. And similarly, all of them will have their own limits. Limit values will be stored in another register called limit register. Okay, and as we said, that these are the registers, one of those n number of general purpose registers that we had right in there. Then we move on to talk about MMU, which I'm not going to discuss at the moment because you don't know anything about virtual address and physical address. We'll talk about all these things later. But just to tell you what it is, that we understood that contiguous memory allocation creates a bottleneck, especially at a time when things are becoming more and more robust. What I mean that in modern software, they are getting more and more robust. So as they are getting more and more robust, so the only thing that we can think of is the more and more robust. So the only thing that we can think of is we need more space in RAM to accumulate those mega software, because the software are now becoming robust. That means the volume of code inside the software, inside this program is increasing. So how do you accumulate all these codes on a simple RAM that's kind of like 2 GB, 3 GB, 4 GB? Well, you can't just expand RAM like your hard disk, because RAM and CPU must go hand in hand. If that volume of RAM is not supported by CPU, then you can't, they won't work together. Right. So there's a reason for that. We'll again talk about it when the time comes. So naturally, we decided to find a way not to implement these contiguous things, to get rid of this contiguous memory allocation. And we moved on to non-contiguous allocation by introducing virtual memory management. Virtual memory management. And in virtual memory management, as I said, in virtual memory management, it was a virtualization of memory. So basically, you break it down into multiple chunks of code and you break it down into multiple pages and you shuffle the pages one at a time. So these codes are grouped together and they just fly in and fly out. That's it. That's one of the most critical chapters in critical part of memory management. Okay, so we'll talk about in more details. And this fly in and fly out needs to be coordinated by someone. This fly in and fly out, as I said, these codes of one single program will not all be loaded at the same point of time right from the beginning in contiguous memory space. Okay, only a part of those codes will be loaded. The rest of them on demand will fly in and the others will fly out. Now, this fly in and fly out is easier to say, but difficult to implement. We need a manager. And that manager is Mr. MMU, Memory Management Unit. It is a unique mapping technique. Again, I go back to that word, mapping technique. We'll learn about MMU in more details in that chapter. That converts the virtual address to physical address. Finally, context switching. Context switching is something probably you already know because I mentioned context switching. Context switching, context switching depends on that how the operating system controls multiple processes on CPU. Remember what I said in the very first lecture, these modern computers, modern interactive computers, these CPUs are constantly getting switched from one process to another process. And that's how we continue to run these multiple processes at the same point of time. And that phenomenon or that process is what we call context switching. So literally, the CPU keeps switching the processes from on the CPU. The first one, the next one, and that's the way to go. Clear? Now let's move on to the next slide. Again, what they are talking about here is relocation and protection. Still, they are stuck with the base register and the limit register, which already we know. Okay, what base register and limit registers are all about. The address location variables use base and limit values. In fact, in the next slide, you will get to understand. You'll get a visual clue. Yeah, there we are. Now, as you can see, a very interesting observation. Now, first of all of you can understand the thing that I mentioned, that each of these programs which are currently loaded on RAM must have a starting point, which is stored as a base value in the base register of the CPU, and must have a limit to the length of the program that is associated with a limit value and that is what we call the limit value, and these two things must be associated with each other. And now, one interesting thing, by using this base value and limit value, each of these programs, they have now their own individual space, which CPU can be aware of. But now if you look at the pictures one more time, you will see a very interesting feature. The operating system in both these cases, the codes of the operating system are dumped at the bottom. Now you may think about that, why at the bottom? Why not anywhere? After all, these are all codes, and we could have loaded them anywhere, not necessarily the bottom of the RAM, bottom part of the RAM, or rather in one part of the RAM. So why do we do it? Okay. So that is something that we need to understand. Well, the reason is, the reason we do that is that gives the level of protection that we want. So say, for example, CPU now wants to read the instructions from a particular address in the memory. If it wants to read a particular address, the first thing that it will check, as you will see in the next slide, the first thing it will check is whether that particular address belongs to OS or not. That is the first thing that it will check. And once it sees that it doesn't belong to the operating system, then it can move on. It can move on to execute it. And then probably it will check whether it belongs to that particular program whose codes it is trying to read or not. So there will be double check. Okay, so that is how the protection that we were talking about in the previous slide, protection, is ensured. Other RAMs, other memories that we have CMOS. There's a kind of like a tiny register, again, not exactly register, but this information, the configuration information, we still need to store. We also have BIOS and ROM. ROM BIOS is the most common one that helps us to boot our computer at the very beginning. That's how we boot our computers every morning when you start your computer. So that is another one that we have. Moving on, disk. That is what we have at the moment. The picture that you're looking at on your slides, this is a picture of your hard disk. Okay? And in fact, if you take your hard disk out, if you crack it open, then will you see all these things? Yes, you will see all the things that you are seeing. You will see all the things that you are looking at the moment. So what do we have there? An arms assembler. Then the arms, a pair of arms for each platter. These are the platters, the disks that you see. They're called the platters. Okay. And then for each platter, we have two surfaces. And all these platters are right in the middle. You can see a spindle there, a round cylinder. Now, cylindrical shape. I don't want to use the word cylinder, and you will understand why very soon. So it's a cylindrical shape that is literally a spindle that keeps moving round and round, round and round very fast. Okay, now that is how your uh, hard disk, literally the physical device, works. And that's what you will find if you crack it open. But now the very interesting thing is, remember this is the hard disk, and this hard disk must be communicated to by operating system. An operating system, as we understand, is all codes. It's a software. So a software trying to do some sort of an interaction with the underlying hardware, right? And that there could be a problem. And we were talking in an earlier class, we mentioned something like mapping, something like microarchitecture, and there it is. If you go to the bottom, you will see three words: cylinder, track, and sector. The cylinder, track, and sector. You can see it right here. Now, will you see if you crack your hard disk, you open your hard disk, will you see a cylinder there? No. Will you see a track? No. Will you see a sector? No. But these are the three important pieces of information whenever your OS wants to communicate something to the controller, the disk controller that controls the disk, the hard disk that we saw just now. So what are these? These are logical interpretation of physical space. If you are listening carefully, you can actually take note of it, note of these expressions. Logical interpretation of the physical space, which we call mapping. Okay? And a software, whenever, and we'll see it in several other spaces, not only here, whenever a software wants to communicate something with a hardware, it must go through that microarchitecture or that mapping or logical interpretation of the physical space. Okay, and much of it actually depends on the purpose. As in a very casual way, remember, I gave you an example of an empty plot of land in front of you, and how do you visualize it? How do you map it? It depends on what you want to do. You want to build a house or set up a garden, you will map the same 100 square meter of empty a plot of physical land in your own way, right? So that is exactly what we do. Moving on, we step into I/O devices. Now, to keep it short again, as I said, all these things that I mentioned here in this slide and the next few slides, we'll be discussing in more details in a better way in chapter 5 when we start talking about input output devices. But right here, we have found all these little things. I don't know why they have sort of dumped everything right here, but I will pick up just the most important and relevant word. And the most relevant word here is the last word, the very last word that is in italics, called interrupt. What is an interrupt? An interrupt is a way to alert CPU that an I/O has happened or is about to happen. Well, I must say it happened. Okay. In other words, CPU, as we already mentioned, is busy in its own computation job, regular computation. So how will CPU get to know that you have pressed the key or you have clicked the mouse? Click the mouse. There's no algorithm in the world to predict when is the next time a user is going to click a mouse or press a key. The only way we can communicate it to the CPU is by generating what we call an interrupt. We use the word interrupt because basically we are interrupting CPU in its computation job and asking it to pay immediate attention to I/O. Because remember, just a few slides back, I mentioned it, that when I/O happens, it goes straight to the buffer, the local buffer, and from the local buffer, it needs to be transferred straight to the RAM. And it must be transferred as quickly as possible. If there's a delay, then what will happen? You type ABC, 5 minutes later, you see ABC getting printed out. We don't need that kind of interactive computer, right? So once we understand interrupt in modern computers, everything happens, all the I/O happens based on interrupts. Now, interrupts is a complicated process, the interruption. For that, we have an interrupt controller that basically controls the interrupts coming from multiple devices, as you can see. Now, interrupt controller will activate, interrupt controller will send a signal, and that signal will basically activate or will get processed by a bunch of code that is called interrupt handler. Again, I'm trying to keep it as simple as possible. Interrupt handler. Interrupt handler is a bunch of code constantly loaded on RAM next to CPU, next to OS. So basically, when it gets activated, kernel is alerted, kernel knows about it, and the kernel will switch the CPU. Okay, and CPU, its prime job is to alert CPU so that CPU will stop doing whatever it was doing at that point of time and pay attention to the I/O. Okay, it's a complicated process, and some of these processes algorithms have been written here. Complete current instruction, preserve current context. You don't have to understand all these or even remember all this. But these are all done by interrupt processing for PC, and this processing is done by none other than interrupt handler. Okay, the interrupt handler. There's the functions of interrupt, nothing more than that. There's this one right here in the corner, as you can see. So the picture B at the bottom, the dispatch handler and interrupt handler. That is essentially the codes that I was talking about. These are the codes that we're running and doing the things in its own way. So that is what we have. You don't have to worry about these processes and technicalities. It's a concept that an interrupt handler in turn will alert CPU, and CPU will switch from whatever it was doing to the I/O mode and will start the transfer of data from the buffer, the local buffer or controller buffer to the memory. DMA, that's another way of doing these I/O in modern computers. Now, why DMA? DMA is a technique, direct memory access, DMA. For that, we need a controller, and that controller is called DMA controller that can serve multiple local controllers, controllers at the same point of time. Now the question comes that why do we need DMA? Well, it's all because the way we interact with the computers in these days. So think about it, that in the past, when the people used to use computers, they used to use computers for serious tasks, not for playing games. But think about you, all your friends all around you, when you guys play games, computer games, and I have observed it. How do you use your input-output devices? But I see the students sometimes crazily hammering, literally hammering with the 10 fingers on their keyboard and clicking wildly on the mouse. At the same point of time, you add more fun to it, their webcam and microphones are working because they're chatting with a friend with whom he's playing this online game, probably. So think about it. How many devices you have activated at the same point of time and what crazy speed you are working on them. Right? So that is quite difficult for your computer to handle. If you still follow the old-fashioned interrupt-driven CPU-based, because interrupt-driven I/O involves CPU, so CPU-based I/O management or input-output management, then what will happen? Your CPU will freeze in the I/O mode, will never ever have time to go back to its original computation-related jobs. It can never go back to the computation-related jobs. It will always stay in I/O mode, taking care of the streams and streams of interrupts which are coming. So your computer will become non-responsive. So we had to kind of free up CPU, and that is what we do in this DMA. As you can see, it reduces the number of interrupts, because when the first interrupt happens, that goes to the CPU, but when CPU gets an interrupt that an I/O has happened, it doesn't take up the job itself. It simply outsources the job to DMA controller. I keep it short right here. Will not explain like they have done. There's no point because we are in the introduction part. It will simply outsource the job to that controller, and for the first time, CPU will hand over one of the most important registers that it holds, and that is the memory register. Its memory register, its memory register will be handed over to the DMA. So DMA on its own can take decisions about finding a suitable memory space for all these incoming IOs. And that is what it does. Okay, that's what it does. Moving on, much of these are repeated. These are the things that DMA will do. They have, again, there's no point talking about these things at this stage, that they have mentioned it, that's okay. These are the same things that we'll be studying in a later chapter. So one thing is for sure, the DMA is a controller. The DMA chip that we were talking about is a controller. It doesn't necessarily transfer any data, but it helps in finding, it does the same job that CPU was doing, literally, but much faster and serving multiple ports or multiple controllers, local controllers at the same point of time, or multiple devices and device controllers at the same point of time. That's it. It just alerts. We just find a suitable address for each of those data, for each of the spending in each of those controller buffers, and we alert the controller buffer will hand over this address to the buffer, and the controller will now transfer the data directly to the memory. So that is what we do with DMA. That brings us to bus, but we won't be spending too much time on the bus. Bus comprises of all these important things. You can see the local bus, there's a cache bus, there's system bus. This bus, as we understand, are the most important communication channels that we have. And for the system bus, we have different architectures like the North Bridge, South Bridge. It's not important in this context because these are all related to hardware. As you can see in this picture, they have the South Bridge, and what do you have in the South Bridge? So the way they have given these slides is more like the students to kind of like memorize things, but that's not the way to learn. If you want to learn about bus, at least you need to look at the real hardware and understand that which is bus, what is the North Bridge, is the north part, what is the South Bridge, and what components are there in those two parts. We will move on to OS components and talk about system calls and operating system structure if time permits. Again, the OS components, as I said, the kernel of the OS is split up into multiple components of modules. These are basically programming modules. Each module or each component will take care of one particular operation, type of operation, like memory management, like what it called, hard disk management. So for each of these components, we will study in more details in the subsequent chapters. For example, first, process management. We'll study it in chapter 2. In the very next chapter, we will study it. Then after that, we have main memory management, chapter 3, memory management. File management and secondary storage management, these two things we will study together in file systems, chapter 4. I/O management, chapter 5. And protection, chapter 6, that is deadlock to some extent. Security is chapter 9, which is out of our syllabus, but if you want, it's on the book and you can study it as well. In terms of process management, again, in this introductory part, without giving any details and setting any context up, they're just giving you the names. So we'll just quickly rush through it. We have a whole bunch of issues to take care of. A process creation and deletion, a process suspension and resumption. Well, suspension, resumption, understandable, because in a multi-programming computer, that's the way the programs run. Constantly switching the CPU, or constantly getting switched from CPU. Right. So sometimes they are suspended, they are in a block state. The block state, it will be moved to the ready state, and ready state back to the running state. It is the resumption. Provision of mechanisms for process synchronization. This is important to avoid deadlock. Interprocess communication, IPC, a very interesting and important chapter with a whole bunch of algorithms in there. But an important topic in that chapter. An IPC is required, literally means when multiple processes are vying, going for the same single resource, shared resource, they need to communicate between each other, stay safe. Then, if IPC fails, we run into deadlock. How can we prevent it? How can we avoid it? Or even if we can't prevent or avoid it, we run into a deadlock, how can we resolve it? Okay, so that is a process tree that we'll mention, but it's not important because most of the modern operating systems, they really don't implement the hierarchy of process in this way. For example, Microsoft doesn't implement it. It's an Unix-based structure, very similar to the next one, pipe, a Unix concept where for sharing of a process, where process A and process B can actually communicate with each other through kind of pipeline. That is a technology. Deadlock, as I said, that we will have in the deadlock chapter in chapter 6, we will have the deadlocks. We will have deadlocks, and for deadlocks, we will first try to predict if there's a possibility of a deadlock. For that, we will have a handful of algorithms. But if we can't predict properly that if deadlock is going to happen, then of course we run into a deadlock and we will have certain ways to deal with that. So basically in deadlock chapter, we'll be talking about three things: prevention, avoidance. Avoidance is a logical way. Prevention is a very crude way of trying to stop deadlock from happening. Avoidance is more important. We will have algorithms for that. If these two things fail, then you run into deadlock. And if you run into deadlock, then we have deadlock resolution. How to resolve the deadlock. What things we can do to get out of that deadlock that has just happened. Right? So we will study these things right over there. You don't have to worry about it. The next one is the same, the deadlock problem. Why deadlock happens? The reason deadlock happens, the simplest of the reasons, is that multiple processes trying to access a shared resource and one of the process, remember this is a Unix scenario inside your computer. I might say that right here, so it will help you to understand why we have deadlocks. The scenario is when it comes to requesting a resource, because resources are limited. For example, CPUs, there's only one CPU. As I said, the multiple processes will be trying to get into the CPU. Always. They are competing for those resources. Now, the key thing about this is when you have a process who has already acquired the resource, and now the other processes can actually request the same resource. Request is permitted, but what is not permitted in real time is that multiple processes can't be inside the same resource at the same point of time. That will create deadlock. Now imagine that one process is holding on a resource and is currently blocked, right? So basically, since that process has been blocked, and this process, the blocked process, is holding a resource, that means that resource is blocked. And others are waiting in the queue asking for that resource. But how can the OS give that one to, to that particular process, the process that is asking for it? No way. So all of them will have to wait for an indefinite period of time. And is what we call that is what we call process deadlock. And that's how we run into deadlock. Clear?
Yes.
Is it okay? Now, apart from the main memory, that takes us to the next part, the main memory management. What we have in the main memory management? In the main memory management, we have a bunch of things. The most important thing, we already talked about it, basically. The most important thing is how do you manage the memory space? How do you manage the memory space? That is the important criteria. Now, how do you manage the memory space? Because memory space is limited. And the memory page, the memory volume is limited, and that should be managed properly. Increase the system performance and maximize memory utilization. That again brings us to the same thing as I already mentioned earlier. Previously, we used to use contiguous memory allocation, and now we have moved on to virtual memory management. And even later, you will see segmentation. So these are all the new things that we'll be studying. Allocate and deallocate memory space as needed. The file management, the next chapter, file management, file systems, file and directory. An interesting concept that in this book we'll never use the word, never use any other word, but we'll always be using directory. What exactly is a directory? Any of you, have you ever seen a directory? Do you have a directory on your computer? Well, I think that most of you understand what a directory is. Directory is what you guys call a folder. The root directory is where everything starts from. So we have the root directory, and under the root directory,
I looked inside to see what's dirty there. I looked inside to see what's dirty.
the root directory, as you can see right here, and in fact, these are subdirectories. But then you look at it and you understand that we are basically talking about folders, aren't we? So these are all folders and subfolders. Similarly, then when we go to the file systems chapter, we will ask you the very question of what exactly a file is. What is your concept of file? What is a file? What is the directory? Now, a folder, if I ask you what's a folder, many of you will say, well, it's a container. It contains some files. But that's not true. It's just another file. And we understand we can't store one file in another file. Right. So it is not a container of files. So we'll talk about these interesting things later. And what is a file? Now, I asked this question yesterday, as I always ask students. and I do get some responses, which are not correct. But most of these responses that come to me are from the user point of view. That means the people say it's a collection of data and it's a place where we keep our data, something like that. But that is what you think it is because you are an user. But in reality, that is not the case. In reality, a file is basically what we call an abstraction of data and behavior together. Okay? And why we call it an abstraction? Because think about it in a very simple way. You break the file and you go deep inside. You break your hard disk and you are trying to find a file that was inside it. Can you really do that in this way? No. That's a kind of ridiculous thing, isn't it? That how can I find the file that I'm looking for by cracking my hard disk and looking into my hard disk? Where is the file? But it is there. But if you crack open your hard disk and you really locate the file that you're looking for, can you tell me where exactly on which platter is your desktop? So what is happening is happening right inside your OS. File system is the component that is responsible for creating this abstraction. All right, so we'll leave it here. Have a little bit of time for your attendance. Please remember, we are right here in the next class. We will wrap it up quickly and jump into a more important chapter, that is process. Right? So all of you, in the meantime, give it a good read. Read it casually, like a storybook, and try to understand most of these things. All right, time for attendance. Xuan Huang, Chi Kang,
Yes.
Vin Phuc, De Quang,
Yes.
Long Ha,
Yes.
Hu Huang,
Yes.
Tan Hum, Tan Hum,
Yes.
Nap, Tan Hum, Napfat,
Yes.
Tan Hum,
Yes. I'm here.
Din Min,
Yes.
Quoc Huy,
Yes.
Yan,
I'm here.
Kim Thak,
Yes.
Nhật Min,
Yes.
Thian Phúc,
Yes.
Wang Huy,
Yes.
Minh Khôn, Duy Bao,
Yes.
Huy Min, Liêm Chúc, Quoc Hum.
Here. I'm here.
Okay, Liêm Chúc, Huy Min, Minh Khôn, Vin Phúc, Xuan Huang.
Yes.
Okay. Check. All right, that's all. Thank you very much. Enjoy your weekend and read the book. And we will get started next week on Monday. We'll finish this chapter and probably we can step into the next chapter. All right?
Yes.
So bye for now. See you on Monday.
Bye.
Bye.
Bye, teacher.
Bye. Good morning. Let's get started. Morning. Let me share your screen. Yeah, so far so good. Sometimes keep running here and there. There's downstairs, there's a Winmart, and sometimes to go and grab something if they have. They don't have it all the time, and I can't go there after 6 o'clock. So naturally,
Yeah.
I don't know when these things will be over. So you guys got vaccinated? All of you?
I got one.
No.
I mean, how many of you got your double 2 shots? All of you got your 2 shots?
Not yet.
Fully vaccinated. Yes, you need to be fully vaccinated, I think. I think that's what they're planning. I mean, that's what I read in the newspaper. If you are fully vaccinated, they will allow you to at least step out on the street. If you're not fully vaccinated, then you are still locked inside your room. That's it. Let's see how it goes. Crazy time. All right, there we are, given the presentation. You can see it. Did anyone remind me exactly where we were the last time?
By
35.
35.
35. I think it was the end of June, probably. Yeah?
Yes.
So we're talking about memory and how many different kinds of memories we have. Well, we group them. As you can see, it's visually quite clear. The last two that we see at the bottom, these are permanent memory. These are permanent storage. These two, these three are volatile. Basically, we put them in this hierarchy based on these things: speed, cost, size, and volatility. Speed and size you can see there. And in terms of cost and volatility, as I said, these three things are non-volatile, and these are volatile, and these two are non-volatile. But even in terms of volatility, register is highly volatile. That cache is less volatile than registers, and main memory is definitely less volatile, a little bit less volatile than cache. And in terms of expenses, registers are really expensive, cache less than registers, main memory on top of that, then below that, and then magnetic disks and magnetic tapes are less expensive. So that is how we put them in the right